Thank you, Michelle. So first of all, I would like to thank the organizers for the invitation. I'm very happy to be here for the summer school. And today and tomorrow, I will tell you a little bit about automorphism of quartic surfaces and Cremona transformation. So let me start by explaining the problem that we want to address. So in general, so first of all, I should say that I will always be working over the complex numbers. And I am interested in the following problem. Suppose that I have X, a hypersurface of degree D in projective space, Pn plus 1. And I want to understand the automorphism group of this hypersurface. So inside this automorphism group, I have a subgroup consisting of automorphism of the projective space that preserve the hypersurface. So I will denote this by out Pn plus 1 x. So these are projective automorphisms that stabilize x. And once they stabilize x, you can restrict to x and get an automorphism of x. And then, well, then we can say, okay, we can ask, are these all the automorphisms or are there more? And so the first theorem that I want to state, so this was proved by Matsumura Monsky. In 64, so this is 64, so they proved this for n at least 2, and then the case of dimension 1 was proved separately by Chang in 78. So they proved that, in fact, with 2 special exceptions, this map is actually surjective. So if, except when, so except when the ND is either dimension 1 degree 3 or dimension 2 degree 4. So except in these 2 cases, this restriction homomorphism is in fact surjective. So all the automorphisms, so okay, maybe here I forgot an important assumption here. I'm always, at least for now, I'm looking at smooth hypersurfaces. So here X is smooth. Otherwise, this is not necessarily true. So this is, for a smooth hypersurface, all, except in these 2 cases, all the automorphisms come from automorphism of the ambient space. And so now what I want to do is let's look at these exceptional cases. So first, let's look at the case when X is a curve in P2. So this is an elliptic curve, and we know very well the automorphism group of C. So this is C has a structure of an abelian group, so it acts on itself by translation, and the automorphism group, so it contains C as a subgroup, acting on itself by translations, semi-direct product with some finite group. Here, D can be 2, 4, or 6. And on the other hand, if you look at the automorphism that are restrictions of automorphisms from P2, these are only finitely many. So this group is infinite, so most automorphisms do not come from automorphisms of P2. And so where do they come from? Okay, so here in this case, the situation is very well understood. They don't come from automorphism of P2, but still, if I consider now Cremona transformations that stabilize C, then these are enough to describe all the automorphisms. So let me introduce here a new group that I will call the composition group of the cubic. So I will denote it in this way so that we don't forget the ambient space. So this consists of Cremona transformations that stabilize the cubic. So once you have such a Cremona transformation, you can restrict it, we call it R, we can restrict it to C and get an automorphism of C. And then a fact is that even though this restriction is not surjective, this one is so. So R is surjective. So all the automorphisms from the curve, they are induced by Cremona transformations of P2. And let me just give you, the proof is easy and classical, so let me just explain to you. So the first thing that you do is you, so let me do idea of proof. So you can, first what you do is you write your C in Weierstrass normal form. So let me just do a sketch here. So I write my C in Weierstrass normal form, so that let me put the origin of the group in the point at infinity. And then here we know how to write down the expression for the translation from a point. So if you do the usual thing, you just to add 2 points, you draw the line through them, find the third intersection point and reflect. So if you do this, you get an expression FP, phi p for the translation by a point. And then if you write down what the expression for the translation is, you see immediately that it defines a birational transformation, a Cremona transformation of P2 that induces the translation. So in this way, we see that all the translations are induced by Cremona transformations, and actually for this finite part is even easier. They come from automorphisms of P2. So, okay, so this is the, sorry, I didn't write much, but I hope this was clear. So this is how you prove this for P2, for a curve in P2. And in fact, maybe now it's good to introduce some more groups. So here, what we've seen so far is that if I consider the composition group of the cubic, then it surjects onto the automorphism group of C. And I can look also at the kernel, and this is usually called the inertia group of the cubic. And in fact, these groups, both the decomposition group and the inertia group, are very well understood. So let me just give you some dates here. So for instance, for the decomposition group, Ivan Pan gave in, so Pan described in 2007 generators for this group. And for the inertia group, Jeremy also described this group in 2008. So this group, so in this case of the cubic in P2, both the inertia and the decomposition group are well understood. And now let's move to the other exceptional case, which is the one that we are interested about. So now, yes? So I would not see, I don't know exactly where they, so you need it to be embedded somewhere. And so I think, okay, it depends on which embedding you were considering. So I have not thought about this for abelian varieties. We will look at them for the next case, which is the case of K3 surface. Yes. It can be very subtle, and it depends a lot on which ambient variety you are embedding it. Okay, but in our case, we want to look at the other exceptional case. So the other exceptional case is the case of when now X is a quartic surface in P3. And so this is the case that we will consider from now on. And in this case here, S is, so it's a smooth quartic surface. For the moment, it is a smooth quartic surface, so it is a K3 surface. And again, the automorphism group of a K3 surface is a very much studied object. It's not as, as straightforward in the case of C. So the automorphism group of S, it may be, in some cases, it is finite, but in many cases, this is an infinite group and can be a pretty complicated group. And while, on the other hand, if you look at the automorphism that come from the ambient space, these are always finitely many. And so as soon as the automorphism group of S is infinite, it is not clear whether or not, it is not induced by an automorphism, and it's not clear a priori whether it is induced by a Cremona transformation. And so maybe this is the question where we are going to start. So this has been attributed to Gizatullin. Okay. So I think the first question is, in this case, let me write it this way, which, we put it as question A, which automorphisms of S are induced by Cremona transformations? Maybe I should say that, okay, the original question was whether every automorphism of S was induced by a Cremona transformation, but we'll see that the answer is no, so let me already state it in this more general form. And okay, so maybe I should write the, let me see, first results. First results were given by Ogiso in 2012. So Ogiso, I think, as far as I know, was the first one to actually address this problem. And so he constructed some very interesting examples. So the first example is he constructed a quartic surface with Picard rank 2, automorphism group Z. But on the other hand, he showed that for this specific quartic surface, that the composition group was trivial. So in particular, no non-trivial automorphism is induced by a Cremona transformation. But then he also provided another example of a quartic surface with Picard rank 3. The automorphism group was much more complicated. In this case, the automorphism group of S was a free product of 3 copies of Z2. So much more complicated. However, for this example that he gave, every automorphism is induced by a Cremona transformation. So this restriction homomorphism was surjective. So these examples showed that the problem very much depends on the quartic surface, and you should not expect a general answer. And now let me just give you some more recent results. Yes? Right. Yes, there's always, yes, correct. So now, so more recent results are the following. So first of all, we have a result from Daniela Paiva and Ana Quedo, and a result of myself with Daniela and Socrates Zikas. And in these works, we completely solve problem A, question A, when the Picard number of the quartic surface is 2. And so this is what we are going to discuss mostly tomorrow. And maybe I should also write another question that we might be interested in. So question B. So we have here, the decomposition group of the quartic surface. And here we already saw that the restriction homomorphism may not be surjective. And the first question then is to understand the image of this restriction homomorphism, but we may also want to describe the kernel, which is the inertia group of the quartic surface. So maybe we want to describe not only the image, but also the kernel. And I should say that even in this case here, where problem A is solved, there is still many cases for which we don't understand the inertia group nor the composition group itself. Okay, so this was the introduction. And so the plan for today and tomorrow is to explain some tools that we can use to attack these problems. And so maybe the tools, I will divide the tools in 2 parts. So first of all, in order to understand the automorphism group, we need to know the theory of K3 surfaces. So the first tool is to theory of K3 surfaces and lattice theory. And here, we will make a lot of use of the Torelli theorem that already appeared in Alessandra's lecture. And the second tool, so this is to understand the automorphism group. But now, to understand the decomposition group, we will make use of another theory, which is the theory that we call birational geometry. Of Calabi-Yau pairs. And so the plan for today and tomorrow is as follows. So today, we will concentrate on the birational geometry of Calabi-Yau pairs. And this will be already enough for us to see some first interesting examples. And then tomorrow, I'll give you a crash course on K3 surfaces, and then I will discuss these more recent results. Okay, so this is it for the introduction to the problem. Okay, so are there any questions here? Yes? Yes, thank you for the questions. Yes, so what happens with Picard number 1? So if the Picard number is 1, then the automorphism group of the K3 surface is trivial. So this follows from the Torelli theorem. And so, of course, problem A is very easy. However, problem B still makes sense. You may still have, you may still want to describe the inertia group, even in the case that it's not clear that even though our automorphism group is trivial, you may still have some interesting inertia groups. But we will see today that no, we will show today that the decomposition group of a K3 of a smooth quartic surface with Picard rank 1 is trivial. So this is one of the final goals of today. Yes. For a smooth quartic surface, yes. So you can use the Torelli for this. Okay, let's discuss this maybe tomorrow when I will be talking about K3 surfaces. So for today, today we are more interested in the second part. So and then tomorrow we discuss K3 surfaces, and then I can discuss your question. Right. Automorphism. Yes. 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 Sorry? And lattices. Theory of K3 surfaces and lattices. So we will use the Torelli theorem to reduce the problem of describing automorphism to describing isometries of lattices. Right, correct, yes. Okay, so now let me move to section 2, which is the birational geometry of Calabi-Yau pairs. So section 2. Birational geometry of Calabi-Yau. And I will be always writing this way, pairs. Okay, so let me start by defining what a Calabi-Yau pair is. So a Calabi-Yau pair is a pair XD consisting of, well, first of all, X will be a terminal projective variety. So I'm assuming that this notion of terminality was introduced in the previous weeks? No? Okay, so it was ever used? Okay. Ah, okay. Okay, maybe I will just say what probably most people said, that this is a mild class of singularities that you are forced to accept in the minimal model program. But okay, I may have to define it formally in a while. Let me not do it for now. Okay, so this is for the variety. Now, the divisor D is just an anticanonical divisor, so it is a divisor that is linearly equivalent to the anticanonical class. And I will also impose some restrictions on the singularities of the pair. And the restriction is that I will ask that the pair is log canonical, so this was probably also not introduced. Again, this is some mild, so here when we look at the singularities of pairs, we are measuring together the singularity of the ambient variety and the divisor. And you can think of log canonical, a toy model for log canonical is a smooth variety with a simple normal crossing divisor. But we will see more other examples as well. So this is what a Calabi-Yau pair is. And I will also, let me make a connection. Okay, let me give you some examples first, and then let me make a connection with Jeff's mini course. So examples. So the first example is the one that we are interested in. It's the case when X is P3 and S is a quartic surface. And here I can either take a smooth quartic surface as in my problem, but I can also allow some singularities for S. So for instance, I can allow Duval singularities for X, or even I could take S to be the union of the 4 coordinate hyperplanes, and this would also work. And this was the one that Jeff considered. So more generally, another example is if you take X to be a smooth toric variety, a smooth projective toric variety. And I take D to be the torus invariant divisor. The union, the sum of the toric invariant divisors. And here, and so this was the case that Jaap was considering in his lecture. And here, whenever I have a Calabi-Yau pair, let me just make this remark. This will be useful. So if I have XD, a Calabi-Yau pair, then there is a unique rational volume form. So let me write n for the dimension of X. Then I have up to scaling, I have a unique volume form on X that does not have any zeros and has a simple pole along D. So there is, unique up to scaling, so let me put it this way, volume form on X. So I denote it by this way, and the space of volume forms, meromorphic volume forms, such that the divisor of this form, that is the divisor of zeros minus the divisor of poles, is precisely minus D. So for instance, in the case, okay, I'll write down some examples soon. Okay, so these are the Calabi-Yau pairs. And now I want to consider them as a part of objects in a category. So let me introduce the relevant morphism between Calabi-Yau pairs. So let me define them. Definition. So suppose that we have, let me write x dx and y dy, Calabi-Yau pairs. And I'll define the relevant morphism between them. So these are going to be birational maps with certain extra properties. So let's start with f from x to y, a birational map. And we say that, so whenever I have a birational map, automatically we get an induced identification between the space of volume forms, meromorphic volume forms. So this will introduce, let me call it F lower star, an identification between the space of volume forms on X and the space of volume forms on Y. Okay, and then we say that F is volume preserving if the forms corresponding to the two Calabi-Yau pairs are identified under F star. So I will be often abbreviated by VP. If this correspondence takes the form associated to dx with the form associated to dy. Okay, so this up to scaling. Okay, up to scaling. Thank you. Okay, so this is the definition, but actually, how do we actually put our hands on this definition? How do we actually check if something is volume preserving? And so let me give you a valuative interpretation for this notion. So valuative interpretation of this volume preserving condition. And this is actually what we will mostly use. Okay, so we have here F, a birational map between X and Y. And it is going to be volume preserving if and only if the following condition holds. For every log resolution of the map, for every log resolution, so I will say what this means. So log resolution, so we have here the map X to Y, and I have here some by a log resolution, I mean a smooth projective variety that dominates both X and Y, and for which, well, if I look at the inverse image of the divisor dx and dy, these are going to be simple normal crossing divisors on Y. So whenever you have such a log resolution, and whenever you have a divisor E on W, then the discrepancies, and maybe here I will have to define what these are because I will need those, the discrepancies of E with respect to x dx and with y dy are the same. And okay, and then maybe if discrepancies have not been introduced, then maybe now it's a good time to recall what they are. And they are the ones that appear in the definition of terminal, log canonical, and so on. So let me just do a quick review what this means. Okay, so let me recall the notion of discrepancy. Okay, so we have here a variety x. So let me take our variety x, and let me take, let's say, a log resolution. So this variety may be singular, but I take here, so, but let's say normal, projective, and then I take here a resolution of x. Maybe I want to take a log resolution. So this is log resolution of xd. So that means that y is a smooth projective variety with a projective, with a birational morphism to x, such that the strict transform of D is going to be smooth on y, and also the inverse image of D is, has simple normal crossing support. So I mean, it's as nice as one can be. And so what is a discrepancy? Now, if you want to compare the canonical class of y with the canonical class of x, how do you do it? Well, this, outside the exceptional locus of x, then on an open subset, these are isomorphic. So this will actually be the pullback of the canonical class, but they will differ by something that is supported on the exceptional divisor. So let me write it in this way. AI, EI, where AI are the exceptional divisors. For pi. So this you can always write. And these numbers, okay, so I wrote it for x, not for xd. I can do the same. Okay, let me just do it already for, since I already wrote this, let me now define what terminal means. So since I'm already here, let me just remind you that x is terminal if all these coefficients here are positive. So these AIs here are called the discrepancies. And now maybe I want to, so this is the definition of terminal. Now if I want to define log canonical or the discrepancy more in general, I have to do this not for x and y, but for, I have to take into account also the divisors. So let me do this. No, I will do the same thing, but I will now compare. Here I have my divisor D, and I can look at the strict transform of D on Y. And then exactly as I wrote here, I have that Ky plus D tilde is going to be equal to the pullback of kx plus d plus a sum over the exceptional divisors of some multiple of E. And this multiple that appears is exactly what I call the discrepancy. So the discrepancy of E with respect to the pair x dx times E. Okay, so it's if you have never encountered this, you should definitely do some computations, and you can, for instance, compute discrepancies for blow-ups over smooth centers, and this is already going to give you some idea of how these numbers behave. So actually, let me give you, since this is a mini course, I think I'm allowed to give you an exercise. And this exercise is so that you understand, have a feeling of how restrictive this, this notion of volume preserving is. Now, let's start with, maybe we can do our case of interest. So we can take x to be P3. And D will be a, say, smooth quartic. But okay, maybe let me do it a little bit more general. Okay, sorry. This might be useful. So let me take just a smooth Calabi-Yau pair, XD, smooth Calabi-Yau pair. And by this, I mean that I want X to be smooth and the divisor D to be also smooth. And now let's assume that I consider some blow up of X, or more generally, if I take Y to X, some divisorial contraction if you're not familiar with that and you're doing the exercise, you may instead to consider a blow up. With some center Z. On X. For instance, some blow up of some smooth subvariety of X. And now the question is, when can we find a divisor in Y for which this divisorial contraction is volume preserving? And this is a very simple computation with discrepancies. So show that there exists a divisor dy on Y such that, well, we want y dy to be a Calabi-Yau pair. And for this Calabi-Yau pair, we want f from y dy to x dx to be volume preserving. So this holds if and only if. So you could consider many blow-ups, but if you want this to be volume preserving, then necessarily you have to have the center of the blow-up contained on dx. Okay, I called it D, contained in D. The codimension of Z in X has to be 2. So this is codimension 2 in X, and therefore a hypersurface inside the divisor D. So these are the conditions on the center. Here, maybe I should assume that, okay, maybe the z cannot be too complicated, so maybe I assume that y is already terminal, so that this already guarantee that y has the correct singularities. So you have to have this condition. And this is if you want to do it for the blow up, it's already, you will already have a sense. So this is a, not necessarily. It could have, for instance, have a very simple, for instance, for a curve, it could be a nodal curve. It cannot be too complicated. So that's why maybe here I am assuming, so let me assume, to be safe, assume that y is terminal. But for the exercise, it's okay if you assume that the center is smooth. Okay, and then in this case, this divisor dy is simply going to be the strict transform of D. Here, it is very important that D is smooth, okay? So otherwise, this is not true. Otherwise, you can have other volume-preserving divisorial contractions, and we will encounter them later today. Yes? Yes. Okay, not necessarily. For instance, you could consider P1 and 2 points, but yes, it should be. In most cases, you can think of them as irreducible and smooth. Any more questions here? Okay, so let me see. Okay. So maybe I should. Let's see how I'm doing time-wise. Okay. Okay, so maybe I should tell you what this has to do with the problem that we were originally interested in. And so maybe this is a fact. It's not hard to prove, but okay. I won't leave it as an exercise, but let me give you a very concrete and simple description of this volume-preserving maps for pairs that are with mild singularities. So if XD is canonical, for instance, X is smooth and D canonical, say X, say P3, sample X P3, and D a quartic with canonical singularities, Duval singularities. Then we can define the group. We can define a group of volume-preserving maps of XD. So this, well, we can define this to be the group of birational self-maps of X that are volume-preserving with respect to this pair. Okay? So this is this condition that we have been studying. But it turns out that when XD is canonical, this is simply the decomposition group of D in X. So these are just the birational self-maps of S that destabilize D. And so this is why this is relevant for the problem that we are interested in. So when we have a quartic in P3, to study this decomposition group now is the same thing as to study this volume-preserving maps. And I should say that an important remark here is that canonicity is really necessary. Remark is that for this fact, canonicity is really necessary. So the simplest example is if you consider P2, XCP2, and the divisor is thus the union of the coordinate lines. So in this case here, the volume form is the one that Jeff explained to us. So this is dx over x, wedge dy over y. And you see, for instance, that the standard quadratic transformation, of course, it will preserve this form, but it does not map D birationally onto D, just contracts the curve. So for the fact, you really need canonicity. So what the fact is telling you is that if D is, say, now a smooth cubic, then the only volume-preserving maps are the ones that stabilize the cubic. So which is not, that send the cubic isomorphically to itself. Okay, so now what have we gained with this? And well, for this 3 weeks, you have been studying Cremona transformations, and you've seen the Sarkisov program, which is a very powerful tool to study the Cremona group. And similarly, there is a special version of the Sarkisov program for volume-preserving birational maps. So notice that in our case of interest, let's say for X, P3, and B a smooth quartic, let me just say a canonical quartic. This is not only a Calabi-Yau pair, but it also, P3 has a structure of a Mori fiber space, so this over spec C is what we call a Mori fibered Calabi-Yau pair. And we have a version of the Sarkisov program for volume-preserving birational maps between Mori-fibered Calabi-Yau pairs. So this was proved by Corti and Kalogiros. So this was 2016. So they proved that any volume-preserving map between two Mori-fibered calabial pairs can be written as a composition of volume-preserving Sarkisov links. So every volume-preserving map between calabial pairs is a composition of volume-preserving Sarkisov links. So let me say, well, I'll try to be a bit precise here to say what this actually means. So I will try to use the same notation that Julia used in her lecture. So when let me just recall the Sarkisov link as let me use this. I hope I will be able to use the same notation as Julia. So this was how she wrote the Sarkisov link. So this is a Mori fiber space. Dots here, and this is the link. So here, for this to be a link, I need that the relative Picard number of L over B is 2. So this was the Sarkisov link as Julia explained to us on Tuesday, I think. So what is a volume-preserving Sarkisov link? So it's the same thing with some extra data. So instead of considering now X, I will consider a Mori-fibered calabial pair. So X1, B1. And here I will also need a calabial pair. So whenever you see a variety, you replace it by a calabial pair. So all the pairs here are calabial. In particular, I am assuming that all the varieties are terminal, all the pairs are log canonical, and the divisors are anti-canonical divisors. All the pairs are calabial pairs, and all these birational maps here are volume preserving for these pairs. All birational maps are volume preserving. So this is what a volume preserving Sarkisov link is. So I think this is the notion that Julia explained on Tuesday. The dots means that this is a small modification. So these are birational morphisms, but these are they are isomorphisms in codimension 1. Yes. Yeah, okay, yes, no, I just used the same one that she used on Tuesday. I looked at my notes. Yes, this was the one, okay, yes, you're right. Otherwise, we could have more stuff, but okay. So this is type 2. Yeah, but this is just to illustrate that what you have to do is whenever you see a variety, you put a divisor so that you have a pair and all the birational maps are. Of top dimension, whenever you see a variety of the top dimension, you put a D. Yeah, the base is not important. Okay, so, I think we can already prove something. See how I'm going to do this. Okay, let me state. Sorry, I forgot the Mori-fibered. Between Mori-fibered, otherwise it doesn't make any sense. Yes, sorry, thank you. So, you were assuming that you have a volume-preserving map between two Calabi-Yau pairs, and you are also assuming that each of these Calabi-Yau pairs admit a Mori-fiber space structure. No. Yeah, well, you need the varieties on the pair to be birational. So but I don't. The base is irrelevant. Okay, so let me state the first theorem, and let's now prove. Yeah, so as we will see, maybe it's good that I will write now the first theorem. What we are interested in is when these Calabi-Yau pairs are P3 with a quartic surface. But we have to allow other Mori-fiber spaces that will appear in the decomposition. So let me state the first theorem and let's prove it, and then I think it will, hopefully it will become more clear. So let me write the theorem A. Okay, so this is with Alessio Corti. I proved it with Alessio Corti and Alex Massarenti. Okay, so let me get the statement. Doing things in a slightly different order than I was planned. Okay, so let me take S, a general quartic surface in P3. So let S in P3 be a very general quartic surface. Then what do I mean by this? So here, by very general, precisely I mean that S is smooth. This is the general condition, is smooth. But I also want the Picard group of S to be induced by the Picard group of P3. This is the very general condition. And the Picard group of S is generated by the restriction of a hyperplane section in P3. So this is the condition. Okay, so then the decomposition group of the pair of the quartic is trivial. And remember that in this case, this is the same thing as the group of volume-preserving birational self-maps of the pair. Okay. So, okay, so let's prove this. Okay, proof. Okay, so let's assume that we have some non-trivial element in the decomposition group. So let phi be a non-trivial element in composition group. Let me write it just to be clear this way. So we know from the volume preserved and from the Calabi-Yau version of the Sarkisov program that we can find a Sarkisov, the decomposition into volume preserving Sarkisov links. So I have here my P3D. Back. Then I have some, say, X1, 1, so on. Then eventually I have to go back to P3B. So let's look at this first link here. And let's describe it. So what can this be? So, of course, we have to start the first link with a divisorial contraction. Call this link name for this. So this first link starts with a volume preserving divisorial contraction. F XD3. But then I gave you an exercise, right? That to show, so from the exercise, we showed that this divisorial contraction cannot be anything, but it must be, the center must be a curve contained on the divisor. So the center of F is a curve C contained in S. And so actually these divisorial contractions, they have been classified. So let me give you just a correct reference here. So this was the divisorial contractions, over P3, or in general in dimension 3, divisorial contractions with center a curve. So they were classified by Ciolas. So this is 2003. So in fact, F is the blow up of a curve. So the first link has to start with the blow up of a curve contained in the smooth quartic surface S. Here we are using, it's important that here we are strongly using the fact that the surface is smooth. The exercise, as I said, the exercise needs the pair to be smooth. And now we will use the second generality condition here to say a little bit more about this curve, because we are assuming that the Picard group of S is generated by the hyperplane section, and it's not difficult to see that from this, so this from the generality condition, so this is from the fact that the Picard group of S is generated by hyperplane section, you show that actually this curve C must be the complete intersection of S with another surface in P3. So C is the complete intersection of S with another surface. But then now we will see that this cannot possibly give you a good link. If you start with a curve that is a complete intersection of S with T, this will not give you a link. So let me write this as a lemma. This is going to be useful also later on. I have departed from my notes, so now I am very lost. Okay, so if the center, if C is a complete intersection of the surface with T, so yes, so this is, let me just say explicit, this is a complete intersection of S with another surface T, then we want to say that the blow up of C does not initiate a Sarkisov link. In other words, using the same terminology that Julia was using, then the blow up of P3 along C over, so let me call this X, over spec C is not a rank 2 fibration. And notice that once we prove this lemma, then this finishes the proof of the theorem, right? Because once we prove this lemma, this is telling us that this first link cannot possibly exist. Sure, but I'm in the case of Picard number 1, so. Sorry? Ah, okay. Then you have to wait until tomorrow. Yeah, very general, yeah. That's okay. Okay. If we have time today, I will tell you today, but okay. This is not the main point. Okay. Okay, so now let me prove the lemma. Proof. Lemma. Okay, or maybe an idea. Okay, proof. And for this, I think I will need me do a drawing here. So let me fix a notation here. So I will call X the blow up of the curve. And I will denote here, so we are blowing up a curve. Let me call the exceptional divisor E. And let me denote by H the pullback of a hyperplane class. And now I will describe the effective cone of X. So now this curve here, remember that this curve here is the intersection of S with T. And whenever you have here in general, whenever you have a complete intersection of two surfaces in P3, the exceptional, the effective divisor, let me make a drawing here, is generated by, well, E. And, okay, here let me put a H. And the strict transform of the surface with smallest degree. So here I will write D. So D is going to be S if the degree of S is less or equal than degree T, and it's going to be T otherwise. Okay, so here is my, so this is the effective divisor. Sorry? Tilde is always, I will always use tilde for the strict transform. So we have here, and now I think I may need to go a little bit deeper into the definition of the rank 2 fibration. So Yulia explained, she gave the definition, she left plus some technical conditions, and unfortunately I do need the technical conditions here. So one of the technical conditions for the rank 2 fibration, let me see if I, let me make a mess here, okay, so let me just write it this way. So X over spec C is a rank 2 fibration. Implies, so she was saying that X must be a Mori dream space, and then one of the technical conditions that she did not state is that the anti-canonical class of X has to be big. So in this case, over spec K. And big means that it must be in the interior of the effective cone, so our canonical class, which is just 4H minus E, must be big. So it must be in the interior of the effective cone. So this tells us that this let me call D, small d, the degree of D, that tells us that the degree of D must be smaller than 4. And therefore, what this is telling us is that this surface here has degree smaller than 4. Okay, so let me write this in the new board. Okay, so from there we conclude that, so the conclusion from this is that B is in fact E, and B the degree of D is less than 4. Okay, so now what I want to show is that in this case we will see that another condition that Julia explained is that one of the conditions in the rank 2 fibration is that any MMP that you run starting with X has to end with a terminal variety. And we will see that this is not the case. If we can run that there are 2 possible MMPs that we can run for X, we could contract the E and then we go back to P3, or you can perform the MMP, say what we call, this is what people call the two-ray game on the other direction. And what this is telling us is that this MMP this other MMP will end with contracting D tilde. And then, so there is an MMP, that ends with a contraction, the contraction say y, x to y, x prime to y prime, the contraction of the strict transform of D. And then one can compute discrepancies to show that this y tilde has worse than terminal singularities. So we'll show, one can show, and I'll tell you how we do this computation. So one can show that this y prime has worse than terminal singularities. And let me give you an idea of how we do this. So the main point is to show that this divisor that gets contracted, the D tilde, is covered by curves of anticanonical degree 0. So for that we show that the tilde is covered by curves C, maybe C, no, not good, curves L with anticanonical degree 0. Okay, so how do we do this? So let me just do a drawing here. So here we have, let's look at this. This is our D. And inside our D, we have our curve C. So C was the intersection of D with the quartic surface S. And now I will consider L to be, I will take big L, a general hyperplane section of P3, general. And I will take L to be the intersection of this hyperplane with D. So this is my L. Okay? And now I will look in the blow up. I will look at the strict transform of L. And we will compute the anticanonical degree of this strict transform. Maybe here I should, to be precise, write L tilde. Okay, so let me see what I want to compute first. Okay, so first let's compute the number of intersection points of L with C. So if we compute the number of intersection points with L and C, so this is just L dot D dot S, and so this is just 4D. And this is precisely the number of intersection points of, this is the intersection number of E and L tilde. All right, I blow up C, and I look at this strict transform, so I just have the same intersection number. Here I'm taking L general, so this intersection is transverse. And now I want to compute the anticanonical degree of L tilde. So this is 4H dot L tilde minus E dot tilde. Okay, so this is just, I can use here projection formula to write that this is just the degree of L, which is the D, minus 4D. Okay, so this is 0. Okay, and once I have this, once I have that this D is covered, this divisor gets contracted, is covered by curves of anticanonical degree 0. It's not, I mean, you need to do a computation of discrepancies, but it's not hard to actually do this from this. So this is the main point, to show that it's covered by curves with anticanonical degree 0. So let me see. Oh. Okay, so maybe I will just state, let me leave theorem A there. And let me just state here okay, I'm not going to give you the proof of theorem B as I had planned, but at least I will tell you how it differs from theorem A. Okay, so what does this theorem A tell us? That if you, for instance, if you want to construct and consider interesting decomposition groups, then you should choose your quartic surface to be special. And then there I wrote the generality condition explicitly. So X smooth, and the Picard group is generated by a hyperplane class. So if you want an interesting decomposition group, then you have to take a special quartic, and you can either take a singular quartic, or you can take a quartic with higher Picard rank. And we can do both. So today, let me just state a second theorem that I'm not going to prove. So again, this is with Alessio Corti and Alex Massarenti. So we consider the simplest singular case. So we, let me state this. So again, let me take, let S in P3 be a very general singular quartic surface. Again, by very general, I mean that, okay, I want this to have a singularity an A1 singularity. So S has a unique singular point of type A1. And again, I want that the Picard group maybe I want what I want to write here. Maybe I want that the divisor class group of S to be generated by the hyperplane section. Then in this case, what do we know about S? So S has a singular point, a double point. So first of all, here we should not consider the automorphism group of S, but rather the birational group of S. So here, let me write so here we have the decomposition group of the singular quartic, and the restriction to now not the automorphism group, because S is singular, but to the birational group of S. And okay, so first thing is that we show, so this, S is singular. So we can project from the point. If we project from the point, we get a 2-to-1 map to a 2-to-1 birational map to P2. But that's not an automorphism of S. It will give you an automorphism on the resolution, but on S itself, it's not an automorphism. So here, this birational group, so this is an involution. This is generated by an involution, Z2. So this is you just project from a point. So this, if you project from a point, then you get a 2-to-1 map to P2. So if you blow up the point, now on the resolution you do get a 2-to-1 map, and on the resolution you get an automorphism. But this automorphism will exchange the exceptional curve with another curve, which is the intersection of S with the tangent cone. Okay, it's not the difficult geometry, but you can show that this is it's a birational map on S, but it's an automorphism only on S tilde. And here we can consider the inertia group of the singular quartic. So the first part of the statement is saying that actually this is surjective, and in fact, this sequence splits. So we write down explicitly a birational, a Cremona transformation of P3 that induces this involution, this birational involution, and this is very explicit. We write it in formulas, and also, so then, the conclusion is that we have this exact sequence, this split exact sequence, and moreover, we have a description of this inertia group, and we can describe this again. It's very it's very explicit, but let me just do a descriptive, just a abstract statement. And this inertia group is a form of GM over the function field of P2. So this means that this is it's an algebraic group defined over this field, such that when you take the algebraic closure, then it becomes GM. And again, the proof, I'm not going to to give you the proof. But the idea, let me just say that the idea is the same as before, as in theorem 1, the theorem A. We just suppose that we start with a non-trivial element here. We take a Sarkisov decomposition, and then we just analyze each link. So you have, start with P3S, spec C, and then, okay, then let's look at the first link. And let me just say what the first link is. So again, exactly the same argument that I did before shows you that you cannot blow up a curve on S. This curve would be a complete intersection with another surface, and then the same argument goes through. However, now, this surface here is singular, and here we have that the singular set of S is a point. And now one can show that if you blow up this point, this still gives you a volume-preserving map. So the first link necessarily is the blow up of the singular point. And so this is a P1 bundle. So this X, the blow up of a point, is a P1 bundle over P2. And then we continue the analysis, and then we look at the next link, and then we show that the next link must be a link of type 2 with a very simple form. You have now this is a smooth, now this is the resolution of S. So now here, we know that we have to start the link by blowing up a curve on S tilde, and then we analyze this. We actually have to blow up a very special curve that is mapped isomorphically onto its image in P2. So you blow up a curve, you contract the strict transform of the cylinder through this curve, and you can do this many types of links, and then in the end, what you do is, after many links of type 2, you go back. The only way to go back to P3 is just by taking this blow up here, and this is what you get. So you get a commutative diagram of this form. And this is what you need to give the description of the inertia group. I'm sorry for this rush in the end and for being over time. Sorry, I will just stop here.
So you have a specific point, which is a singular point. You can project from that point on P2. You
Yes.
get a pencil of lines.
Right.
And are you saying that, so this group is preserving this pencil? That's what you are saying?
Yes, exactly.
Yes. And then the quartic surface is a double section of this.
Exactly, yes.
But then your GM preserves the 2 points in these double sections.
Right.
So is it GM over CP2 or over something which is like a quadratic extension of
The
CP2?
quadratic extension,
Okay,
yes.
so when you
Okay, there should be a square here.
Yeah, yes, it's over a quadratic
Yes,
extension given
yes.
by your quartic surface.
Yeah, exactly, yes, yes. That's exactly how we... Here, yes. Yes, so from here, yeah, so this description comes from this middle square here. Sorry? No, no. It is the resolution is a K3 surface.
So this is something we saw yesterday in the talk of Emmanuel.
Right, yes.
For these Borel subgroups, in dimension 2,
Yes.
the quartic is where a curve and so on.
Yeah, exactly. So actually, I should say that we write down explicitly so if you start with a formula for S, you write down a formula for every single element in the inertia and the decomposition group exactly by using these quadratic forms.
In this inertia decomposition sequence, if you take, say, as a quadratic surface in P3, a smooth one, so if you look at the aberrational sequence, do all elements of the Cremona group acting on P1 times P1 lift to birational maps of P3.
Okay. So I haven't, well, we haven't, so many of these techniques that I explained today, they can be used to study any Calabi-Yau pair, but you need a quartic so that you can use this. So if you don't use a quartic, but if you're interested in the quadric, then okay, then of course the automorphism group that comes from automorphism of the ambient space. I don't know if you could use this type of tool to understand the birational map. So I don't know, I haven't thought about this. You cannot directly use these techniques because these are only for Calabi-Yau pairs, but you could try to use the usual Sarkisov program. But I haven't looked at this case.
I mean, in the theorem of Corti and Araujo, is it really for minus kx or positive multiple of minus kx? I'm interested in the case that P2, and you take a sextic with 10 double points. There is a huge group preserving not the volume form, but the section of minus 2k.
I don't think that they're, okay, I don't. Yes, so yes, I don't know if their theorem extends to.
Actually, I'm working with Figueroa and Nada over the case.
Okay. Okay.
In this case, you need to consider rational coefficients, so we prove that Cremona Sarkisov formula for either index of the outcomes.
Okay, so you do have some tools, yeah.
Yeah.